Welcome to section 13.2, planning a geometry proof. This little cartoon exemplifies the journey that we're about to embark on, and I really like this. I think it's really applicable to creating geometry proofs. So you can see in the cartoon that there are two men. They look like maybe mathematicians. There's definitely math on the board, and you can see the math in the top left corner and the bottom right corner, or the left and right sides of the board, and somewhere in the middle, right, it says, then a miracle occurs. And the professor, let's say, or one of the men, he says, I think you should be more explicit here in step 2. Well, this directly applies to math, right? Teachers are always telling you you need to show your work so that we know how you solve the problem. And in this case, there's a big chunk of work missing, right? So especially with what we're going to do and what we're going to learn about creating geometry proofs, every step of the problem-solving process must be shown and explained. And if you don't do that, then you don't have a good proof. So here are 4 steps for writing a proof. Step 1, identify what is given and what you must show. Step 2, transfer information onto a diagram. Step 3, organize proof by thinking through the problem. And finally, write a proof. So let me talk about a couple of these. So in step 1, identify what is given and what you must show. Every proof will start with some sort of given information, right? And what you must show is the thing that you have to end up proving to be true. Now in step 2, they talk about using a diagram. Using a diagram in a proof can be very helpful and sometimes can be essential. The diagram becomes a part of the proof. A diagram must be part of the proof in some cases. Not in all cases, though. Step 3, organize the proof by thinking through the problem. So this is where all the work really starts. You cannot start to write a proof until you have built the argument of the proof in your head. Now, it may not be perfect in your head, but you can't start writing things on paper. You can't start writing the argument down on paper unless you already have a sense of the argument in your head. When I say the argument, I'm talking about the steps of the proof. And then step 4, actually writing the proof. I'm going to talk here in a second about different formats of writing a proof. And oftentimes when you start to write a proof, you need to go back and revise it, and perhaps more than once. Okay? Creating a geometry proof is, if you're doing a good job of it, is a very thoughtful and oftentimes a pretty rigorous process. So these are the 3 types of proofs. The 2-column proof, where the column on the left contains the steps of the proof, and the column on the right contains the justifications for why each step can occur. Number 2, a flowchart proof, where the steps of the proof are contained inside boxes with the justification underneath the box. And step 3, a paragraph proof, where the steps of the proof and their justifications are written in a paragraph. So we will work with all 3 types of proofs. We will create all 3 types of proofs. So let me show you some examples. Here we're being asked to write a proof in each of the 3 formats. And this is actually going to be an algebra proof. Algebra proofs are very straightforward. They're very easy to introduce proofs because you guys know algebra. So the given information is the equation 2x minus 15 equals 25. And we need to prove that x equals 20. So let's sort of go through the solving of this real quick. So 2x minus 15 equals 25, right? We would add 15 over to the other side, and we will get 2x equals 40. And then we would divide both sides by 2, and we would get x equals 20, right? This is basic algebra at 1, solving an equation, and that should make complete sense to you. Now, Those are, in a sense, the steps of the proof. But each step has to have a justification. So let me show you a proof in two-column format. And understand that these are very simple. This is a very simple example. So this is a two-column proof. You can see the column on the left has the three steps that I just went through in solving for x. And the column on the right shows you the justification for why each step can occur. For example, in step 1, that was the given equation. So we state it as given. It's given information. Step 2, remember we added 15 to the other side? Well, this is actually the addition property of equality, where we can add the same value to both sides of the equation without changing the solution set. And then to get step 3, we divided by 2, and this is the division property of equality, which tells us we can divide by the same thing on both sides of an equation without changing the solution step. So we have each step and each justification for why each step can occur. Now let's take a look at a flowchart proof. Let me remind you, this is a very basic flowchart proof. You can see that in each box is each step of the proof. And under each box is the justification for why each step occurs. Now we'll get into some very elaborate flowchart proofs where we will have arrows flowing from one box to multiple boxes, and this will be a great exercise of having to rethink and revise your proof, because very often we don't get the flowchart proof right the first time. Now, in this case, it's very simple. You can clearly see how one step leads to the next based on the arrows shown. And finally, a paragraph proof. Given 2x minus 15 equals 25, we add 15 to both sides of the equation using the addition property of equality to get 2x equals 40. Then we isolate x using the division property of equality and get x equals 20. I have put each step and each justification into a nice, clear, flowing paragraph with correct punctuation, nice transition words like then, next, maybe use the word like finally, and it flows in nicely. It reads just like a paragraph should read. So that's a very brief introduction into the three different formats of a proof, and we're going to embark on a journey where we're going to work a lot with proofs, and we're going to become some good problem solvers throughout the process.